Okay. Well. Electric field KQ1 over R squared, how much work move charge capital Q from R1 to R2? Okay, well. Work. Is integral force with respect to position. And what's that? And this is force. All right, F of R force is a function of R. So. Moving this charge. The force is this charge times the electric field. Well, the rest is really simple because it's a simple integral. Integrate from R1 to R2. K. Q1 capital Q over R squared dr. K Q1 and Q factor out, you get the integral of 1 over R squared, which is negative 1 over R. So it's I'll write the capital letter in front. And then it's going to be 1 over something minus 1 over something. Then you want to be careful to get R1 and R2 in the right position. It's going to be negative 1 over R squared. Okay. So 1 over R squared would be 1 over R2 minus 1 over R1. Negative 1 over R squared would be 1 over R1 minus 1 over R2. Okay. Makes sense. Simple integral. And of course, I gave you numbers. Preferable. Just do it symbolically, then plug in the numbers because you might have several sets of numbers you need to plug in the situation. Okay. Okay, well. Excuse me. You allow if your season comes along. Everybody else get that information. There's fixed Q1. Okay, there's movable Q. And if you can call that a test charge. So we're talking about moving from R1 to R2. We see again work going from 1 to 2. Is this. Okay. This is what it is. Okay. Voltage 1 to 2, which is potential difference. For test charge from R1 to R2. Work per unit test charge. Okay, and what would that be? Okay, so V12 is test charge, big unit test charge. Okay. Now, we've dealt with identical intervals when we dealt with gravitation. Okay. Talk about the difference in gravitational potential energy. That'd be a big G, big M over R squared instead of a Q1 over R squared. But the gravitational potential energy of the of a given mass, then you use M instead of Q. You have the gravitational pull of the Earth. You have mass, and you have a big G, big M, little m over R squared here. It will come out the same. You just have a G, big M, little m out here. Okay, so by analogy, you should have a good context for understanding this. Although I did ask one question about mass moving away from the moon toward the Earth on the exam, people didn't do very well. Okay. So you want to make sure you kind of lock in that idea. Go back to the analogy of gravitation. You understand what I just said, and that's good. Okay. But you have to apply it. So I'm just saying, oh, it would have been good if you would have been able to apply it really well there. There's a lot of stuff going on. And you made up for it real well with simple harmonic motion control class. Okay. So, you know, they're trade-offs. So that's important. As is simple harmonic motion, you need simple harmonic motion to do waves. Okay. And you need that other thing to do this. Well, you understood what I just told you. I'm sure I saw a lot of understanding in your eyes. Okay. Give you better. Okay. So it's very totally analogous. The only thing that isn't totally analogous is that you can have like or unlike charges. With gravity, you always have a negative out front here because it's always a force of attraction, as it would be if you have opposite charges. They can be equal, or they can be a like sign or opposite. Okay, so anyhow, this V12 there's potential difference. What are the units? Write down the unit, the SI unit of this potential difference. Okay, what are your units? Well, what are the units of your force? Your force units, that's newtons. Okay, so what's the unit of your work? Well, you're integrating force times distance. Force times distance is newtons times meters. So this is in Newton meters. Or joules, whichever way you want to write it. Somebody wrote joules, somebody wrote. Okay. So what's this? You're dividing work by charge. So you're going to get joules per coulomb. Okay. Or Newton meters per coulomb. Not only one person actually had Newton meters per coulomb. Okay. I saw Newton per coulomb. I saw something else that was being reasoned out all the way back to the formula, and I didn't really give you time to get that right. Okay. But the ultimate answer here is works in joules, and this is work divided by charge, which is going to be joules per coulomb, which is also Newton meters per coulomb. Okay, so in SI units, so all this is really very simple, isn't it? Okay, so now you know what a volt is. That's unit of potential difference. Okay. So I don't know. That noise is worth having hot water in our water fountains for. With water fountains in our fountains anymore, you got to carry something around to catch it. If you don't have anything to catch it in, I guess you die of thirst. But at least you die of thirst with hot water. No, it's pretty neat having hot water. And that's going to be handy in the lab. And we need hot water. I don't know how hot it would be. We probably would need that much hot water. But there are times in that we do use it. We don't have running water in here. One of the things that we lost when we moved the physics lab. Okay, so so that's what volts are. Okay. So I'm going to give you a little preview. An amp is a coulomb per second. How much energy required to ten amp current through under 10 volts. One minute. I just added a hint here. How many coulombs goes through how many volts? And a volt is a joule per coulomb. You know how many coulombs through how many volts, you can figure out how many joules. Well, reasoning this out, you got 10 amps. Coulomb per second. Okay. 60 seconds, this is 600 coulombs. Okay. Got a lot of energy. Well, I weigh something a little over 700 newtons. Okay. I'm talking 750. We'll just say 800 because it's an even number. My boots are heavy. I think by the time I'm in my usual attire, pretty close to 800 newtons. So 800 newtons. You climb how many meters with that much energy? Well, every meter is 800 joules. If I'm going vertically, you're climbing against gravity, right? And 800 goes into 64,000. Okay, 80 times. So somewhere around 80 meters. 100 feet. All right. How long should it take me to climb that far? Well, without straining myself, I climb about 7 meters per minute. Okay. And I can do 10. You get pretty out of breath, not comfortable, and maybe not sustainable for a whole long time. 10 minutes, yeah, an hour, forget it. Okay. So yeah, that's about half of what I could do in my prime. It's quite a bit less than what any of you could probably do. You're younger and not as much of your energy is turned into brain power. That's what happens when you go. Yes, everybody's laughing. But silently, because we don't really do as we can. Okay. Now let's see. Okay. So anyhow, so to climb 80 meters, take me under 12 minutes. I don't want to strain this. I'll get mildly out of breath by the top. Okay. Try doing it in 8 minutes. I can do it in 1 minute. Okay. And that would make you mildly out of breath. Okay. So there it is. That's just relating to, you know, what your appliances will do if you just plug them in to what you can physically do. In a minute, this thing's going to use as much energy as you can reasonably produce in 6 minutes or so. You wouldn't be able to power that for very long. It'd be a horsepower and a half. Which is about 15 times what people can sustain from 8 hours a day. Okay. And you know, kind of want to make those comparisons. You can have a little bit of a sense of what these numbers are. Okay. In symbols, well, it's simple. The symbols are well, let's ask how much power. Okay, everybody knew the got it, let's do it. Power, of course, is amount of work per unit of time. Put it all over the average power. This is 66,000 joules over 60 seconds. Which is 1,100 joules per second, that's 1,100 watts. How much does the power cost you? Oh, around here, it's something over 10 cents a kilowatt hour. Okay, well, 13 cents. I don't pay that much attention. I know about what it is. You know, what my electric bill is. But I don't keep track of it. Right. That's also I checked a couple of years. 1,100 watts. Okay. You pay about 15 cents per kilowatt hour. 15 cents, 1,000 watts for an hour. Okay. And this is just a little over 1,000 watts a minute. Enough energy. Climb. Couple hundred feet. Okay. So that's 1/60th of an hour. So that much energy costs you 1/60th of, say, 12 cents. Okay, 0.2 per second. Shows you what our power is worth. Okay. As opposed to power that we can generate by rotating coil in a magnetic field. Or magnetic field in coil. Okay, again, you want to kind of keep those numbers and those ideas in your mind as we move on into potential difference this week. Okay, capacitors next week. And circuits after that. We're going to start dealing with circuits and that on Friday. So you want to have all this clearly in your mind on Friday. Now, of course, this current that we get from 110 volt outlets isn't created by static charges. It's not electrostatic, and we're doing electrostatics, right? It's created again by rotating coils within magnetic fields and magnets. So I'm going to just kind of turn to electrostatics. If you keep this in the way, like more things. But we can say, we can formulate all this. You don't need formulas to figure this stuff out. Now, there's a point at which you need formulas. And when you start doing those magnetic fields inside the coils and so you better be able to use the formulas. But the formulas that we get out of this that are worth remembering, that your first recourse ought to be just your intuition, and you did fine with your intuition. You were able to answer these questions. Okay, sometimes, you know, with a little glitch. It's work per unit charge, not force per unit charge. That's what, you know. It's like voltage is work per unit charge. But if you understand the definition of voltage, that's just the definition. So understand intuitively, work per unit of charge. You're going to get used to that, and you want to get used to it. Okay, and you both might have a formula with different one. Yeah, with conditions on it and everything. Okay. But that's going to suffice for right now. And Average power working with another team, which would be usually overdone too. Okay. You can write that as a formula, but you don't start by memorizing that because it's really one step easy to understand if you've got the background, which you have. You would have to answer the question. Okay. So that's kind of it. Now for point charge. Okay, point charge Q is just what we did. I called it Q1 before. But now we understand big Q is going to stand for test charge. And it could also stand for an actual charge moving through a circuit. Okay. Or could be any charge. This is potential. Now, I'm going to move to the different situation. What's your potential? Potential due to an infinite feeder charge with density sigma. Relative to the sheet. One more thing I should have said here. This is then equal to the integral of the electric field times dr. E being the electric field of this point charge. Okay. Because E is just, well, you're integrating QE over Q. That's what this really is. Okay. So this thing here. And of course, we talked about that. Okay. So it's another thing to look. pulling the whole idea of the electric field, because you're gonna want to do this one in terms of the electric field of that sheet of charge, which you ought to be able to work out using Gauss's law instantly. Maybe not. So I'll give you a minute to puzzle on it, and then I'll re-explain that, because that's something we just learned last week, okay? Okay, somebody of you looked up or remember the formula for the field of an charge. Okay, maybe 2 sigma over something like that. I don't even remember. I don't even want to remember it, because driving instantly is very simple. You picture again. Well, just demonstrate. Okay, imagine this is your Gaussian surface, and your sheet is your infinite sheet of charge. Got me at 2. Okay, I'm imaginary also. Well, actually, it's a sheet of charge, it's imaginary, I think. Okay. Now, this thing has an area, cross-sectional area. And if you multiply that cross-sectional area by sigma, you see how much charge is enclosed in this thing, right? Okay. So the charge enclosed here is sigma times cross-sectional area. Okay. The Gaussian surface sigma times its cross-sectional area. Your Gaussian surface has to be a cylinder, doesn't have to be round, any cylinder, or it could be a prism, right? So, right. Okay, a polygon, that's bounded, or some combination of piecewise polygons, marks, doesn't matter. Doesn't matter what the boundary is, as long as it's got a boundary. Okay, and extends then perpendicular to the infinite sheet of charge. It's got a cross-sectional area, and it's got a length, but that doesn't matter, because the other thing is the field of the infinite sheet of charge by symmetry has to be perpendicular to the sheet. So the field exits the surface only out of the ends. So all the flux is through the ends. I'm not writing down all the conditions. It should be implicit that this thing is perpendicular from either a cylinder or prism, perpendicular to the sheet of charge. Okay, flux is through the end. What's E times cross-sectional area? There's 2 ends, so you're going to double that. Now you could do it just through one end. If you really want to, you can just take this thing up to the sheet and stop there. It only encloses half the charge on this area. The other half's on the other side of the sheet. Okay. If you imagine an infinite conductor, okay, half the charge is on this side, half the charge is on that side. So in that case, this would cut half of it, and you would only have cross-sectional area on the. But in general, that's what you're like. Okay. There's your universal. relationship. Or pi k sigma times the cross-sectional area. So, well, this is equal to this. You got a 2 here in the cross-sectional area. So you divide both sides by 2, you get 2 pi k m. K equals 2 pi k sigma. Okay. And that equals, since k is 1 over 4 pi epsilon naught, sigma over 2 epsilon naught. You should be able to convert quickly between k and sigma. But keep that in mind. Not between k and epsilon naught. K is 1 over 4 pi epsilon naught is 1 over 4 pi k. Again, if I'm doing calculations, I like k better than epsilon naught. Because k is a number that's really easy. If I'm doing stuff in my head, I want k. All right. Well, there we have it. So what's your answer? Potential movement of differentiating charge at density sigma relative to the sheet. Sheet charge density sigma. Assuming sigma is positive, if it's negative, the arrows reverse. All the arrows have the same length because it doesn't matter how long this tube is. By the symmetry of an infinite sheet, the field is always straight away from the sheet. If it wasn't, rotating the sheet would change the charge, but a rotated infinite sheet is just an infinite sheet. And if the charge is uniform, which is assumed implicitly. So everywhere in the universe, this infinite sheet would have constant electric field straight away from it. Now, there's no such thing as an infinite sheet of charge because there is not an infinite charge in the universe. So it's an approximation. It works just fine for a finite sheet. If this blackboard is a finite sheet, then at this point here, but this far out from the board, it might as well be infinite. Because contributions of the rest of the charge to the rest of the vicinity would turn out to be negative or close to negative. And that's again because I symmetry field is straight away. As long as the field is straight away from the board, from the sheet, even a finite sheet, this model holds. Okay. Now, if I go out to the end of the room, this is no longer going to simulate an infinite sheet. The field is not directly away from it, or at least not perpendicular to it. Okay. This thing becomes a point charge by the time I get out there, it's closer to point charge than it is to an infinite sheet. And then everything's radial. Even if I go up there, it's in this direction, down there, it's in this direction. So this doesn't hold. And now your flux is escaping through the sides of that long tube. It's not escaping through the ends. I mean, some of it is. There's a lot of escaping through the side. So, and it also decreases in magnitude. All right. So we have this, so my question is, equals 2 pi k sigma. You might like sigma over 2 epsilon naught better because it doesn't have pi in it, it's less confusing. So you can make your choice to be able to do either way. What's potential? Now, potential is relative to the position of the charge. So you want to calculate the work. So this is your reference point, V is 0. Okay. Now we move out to point here. How much work does the electric field do on a test charge as we move from here to here? Here's point. Okay. Does it matter how we go from here to here? So one of your principles is, this is a conservative field. Okay, you're gonna find out in multivariable calculus pretty soon. A conservative field is fine. Okay. It's equal to the gradient of a potential function. Well, you're gonna see gradient, I think this week. So we can even talk about it in that class, which will give you more grasp of what this is, okay? And we also do a line integral of a gradient of a field. Turns out that it doesn't matter what path you take between the two endpoints. Well, that's multivariable calculus. But you're going to see very clearly, I hope, within the next 2 weeks, you will understand why it doesn't matter what path you take. Okay. We know from first semester that a conservative field is a path independent field. Okay. So you could calculate the field if you had a parameterization of this function. Pretty easy to do if you got a parameterization. However, probably easier calculate it along this path. Okay. So what do you need to know about this path? If you know the point, if you know the coordinates of this point. Now let's say that your infinite sheet is on the line x equals 0. Right? Or it's the plane x equals 0 in an XYZ coordinate system. X this way, Y this way, Z that way. Right? So let's say that this point is in rectangular coordinates. This XYZ. Now, what coordinate changes as we go from here to here? Whichever way the fingers. It's the x coordinate that changes. And Y and Z, they just got parallel planes out here, they don't matter. So Distance from here to here is X. How are you going to calculate the work done on a test charge capital Q from here to here? What's the work of test charge Q? Capital Q. Okay, so what's the work of test charge Q? Well, what was that piece of chalk? Too low on the board, okay. Okay. The same thing we did over here, except it's easier, is over here. Your force varied with R. Here, your force doesn't vary at all. And so what's the force? Okay, well. Force equals QE. And well, I'm going to be careful about my directions. Force here would be QE times the J vector. That's your y direction. Direction this way. So here we're going with y. Here, yeah, we got to do this part too, because that's going to be the reason. Okay, force is QE times J. M E. There's 2 pi k e at 2 pi k sigma times. Okay. Let's go ahead and play that. Okay, so that was here. Half through delta x. The displacement is from x equals 0 out to x equals 0. That's equal to. That's good. Distance is x. Delta x is x now. Well, delta x is QE times x. That's the work. We'll say from 0 to 7. 0 to 3, maybe. But that's from the infinite speed out to the. Well, I say it's out to the 30 feet, but I haven't really finished. Why do I say it's the work from here to P? So the path in the y direction is this. I'm going to say that's the work from reference point out to X. Then the path X, Y, Z, compare to X, Y, Z. I could clutter this up with some notation. Let's call this point B. Now let me treat my notation here again. Then I'll just call this the path. Okay. Path from here to here. Well, delta S is YK. And think of this, but I didn't. Call this the order. Call that your reference. Okay. So what we're saying is my reference point, which is the origin, to any point X, Y, Z, we can draw a path parallel to the y-axis. Delta S and X check. Then from here to here, draw path point P, that's ZK, not Y. Doesn't matter what it is, because F dot delta S this is zero, so J dot K is zero. Now, intuitively, you're going this, there's no force in the direction of your path. So you get zero work from here to here. Here, you just get the magnitude of the field times the length of this part of the path. Okay. So work from 0 to P equals 2E times X. And V from 0 to P 2EX over 2, which is just E times X. All right, well, that's relevant. So now here we've got a capacitor. Now we're anticipating something's coming next week, but here we got a capacitor. And we got some distance between the plates. So we've got some charge signal on this plate, some charge signal on this plate. This plate, let's say this plate's positive. Going to give you a charge of 2 pi k sigma in this direction. Okay, and then this will be negative. It's going to give you another 2 pi k sigma again in this direction, because field from a positive plate is going to go away from the plate. The field or negative plate is going to go toward the plate. Okay. Now outside the plates, you've got two pi k sigma. Actually, we couldn't get that out. 2 pi k sigma toward the negative plate and 2 pi k sigma away from the positive plate. Now you got pictures in your book. That's how that looks. Okay. Very simple. Field cancels out outside the plates. Pretty much. You got some edge effect and stuff like that. So it's not totally zero outside the plates, but at any significant distance from the plates, you have essentially no electric field. But between the plates, you got a strong field. The potential difference between the plates, the voltage between the plates, is 4 pi k sigma field times the distance between the plates. So this is relevant. And I can complete what I wrote down there. This E times X is sigma times X. Again, in a capacitor, you double that because of the two plates. So you understand that much? You got a pretty good start on the idea of potential difference.